The fifth and final learning objective in section 3.2 is to apply the 68, 95, 99.7 rule to estimate proportions and probabilities and to find cutoff values. Here's the first example. At a tennis tournament, a statistician keeps track of every serve. The statistician reported that the mean serve speed of a particular player was 97 miles per hour, and the standard deviation of the serve speeds was 11 miles per hour. Assume that the statistician also gave us the information that the distribution of the serve speeds was bell-shaped. What proportion of the player's serves are expected to be between 86 miles per hour and 119 miles per hour? So, what the 68, 95, 99.7 rule tells us is that if we have a bell-shaped distribution, which is why it was important for the statistician to tell us that, then we can label where the mean is, and we can label where 3 standard deviations above the mean and 3 standard deviations below the mean are. And then we know that 68% of the data is within the first standard deviation. 95% of the data is within 2 standard deviations. And 99.7% of the values are within 3 standard deviations. So let's figure out what these values are for these vertical lines I've drawn. The mean, which they told us, is 97. I'm going to put that in the middle, in red. The standard deviation, this distance between lines, is 11. So I can label this. 97 plus 11 is 108. 108 plus 11 is 119. 119 plus 11 is 130. And then I can label the lines to the left of the mean. 97 minus 11 is 86. 86 minus 11 is 75. And 75 minus 11 is 64. So this question asks, what proportion of the player's serves are expected to be between 86 and 119? So that's from 1 standard deviation below the mean to 2 standard deviations above the mean. So from 86 to 97, I have 1 standard deviation. And I know that from 86 up to 108 is 68%. That's what the 68, 95, 99.7 rule gives me. So from 86 to 97, which is just half of that area, I have half of 68%. That's 34%. And now I want to go from 97 up to 119. That is from the mean to 2 standard deviations above the mean. I know that from 75 to 119, there's 95%. That's part of what I labeled. But I only want half of that to get from 97 to 119. So I'm going to take 95 and divide that by 2. And that gives me 47.5%. So then if I add 34% plus 47.5%, I get the total percentage that I want, which is 81.5%. That's the answer to my first example here. Let's look at another example. The mean lifetime of a tire is 30,000 kilometers with a standard deviation of 6,000 kilometers. About 95% of all tires will have a lifespan between what 2 distances? So I'll draw my bell-shaped curve again. That wasn't very pretty. Let's try one more time. Maybe a little bit better. In the mean, I'm going to put in the middle, I'm going to put the mean, which is 30,000. 95% I know is within 2 standard deviations from the mean. So I'm going to take 30,000 and add 6,000 2 times. 30,000 plus 6,000 is 36,000, and then another 6,000 added on to that, is 42,000. And then I'm going to take 30,000 and I'm going to subtract 6,000 two times. So 30,000 subtracted 6,000 is 24,000, and then subtracting another 6,000 is 18,000. Okay, so the way that I got these two values is I took the mean and I added 2 standard deviations, and that gave me 42,000. And I took the mean and I subtracted 2 standard deviations, and that gave me 18,000. And I knew to add and subtract 2 standard deviations because it gave me 95%, and the 68, 95, 99.7 rule tells me that 95% of the data values will be within 2 standard deviations. What percentage of tires have a lifetime greater than 42,000? So we've already drawn this picture, and 42,000 was here, 2 standard deviations above the mean. I want just this area that is greater than 42,000. Well, we already talked about how this area here is 95%. The whole thing is 100%. So if I have 95% in the middle, then I have 5% left, and half of that, 2.5%, will be in that tail, and 2.5% will be in the left tail. So the answer, the area in the right tail, is 2.5%. And I have one last example. Avoiding an accident while driving can depend on reaction time. That time, measured from the moment the driver first sees the danger until they get their foot on the brake pedal, is thought to follow a normal distribution with a mean of 1.5 seconds and a standard deviation of 0.18 seconds. What reaction time is the 97.5th percentile? Report time to the nearest hundredth of a second. So I'm going to draw my bell-shaped curve again. And in the middle, I'm going to put the mean of 1.5. If I label my lines, 1 standard deviation above the mean is 1.5 plus 0.18, which is 1.68. 2 standard deviations above the mean is 1.68 plus another 1.18, which is 1.86. And that's actually the value that I want, because I know that if this is 95%, this area here, which we just talked about, has 2.5%, which means that the area below it is 97.5%. That's what a percentile means. And so 1.86 seconds is the 97.5th